Okay, so the fourth talk in this session, final talk for this session is, is from Cheng-Yang He, who's a PhD student at Northeastern, and it's going to be about efficient scheduling and collectives, which is a common structure in some of these types of systems. So over to you.
Okay. Good morning, everyone. Thank you for being here today. I'm Cheng-Yang He from Northeastern University. And it's a pleasure to introduce you to ResCCL, Resource-Efficient Scheduling for Collective Communication. And to set the stage, let's talk about the background. As distributed training systems continue to scale, collective communication has become a major bottleneck. The figure on the right shows that as cluster size increases, collective performance drops significantly, and the GPU utilization follows suit. On the left, the NIC egress traffic pattern further highlights the inefficiency of current communication strategies. While existing solutions try to optimize collective communication through better algorithms. Here, algorithms refer to communication scheduling. They overlook a critical constraint, poor execution scheduling. Execution scheduling is what happens when theoretical algorithms are developed onto actual GPU clusters. And this leads to suboptimal performance even for theoretically optimal algorithms. Increased thread overhead and unwanted interference with computation tasks. Clearly, there's room for improvement, and this insight is where ResCCL comes. Let's take a quick look at the landscape of existing work. Vendor CCL like Nico and Rico, designer and synthesizer solutions like Taco, Tico, and SIGCOMM', as well as domain-specific languages like Mexico language have great strides in improving communication algorithms. However, these solutions fall short when it comes to efficient execution at the runtime level. At a high level, these systems optimize the algorithms to a backend CCL layer, which eventually executes using primitives like send, receive, and receive copy. Current collective communication libraries, such as Nico or Mexico, typically operate at one of two granularities in runtime. Both execution styles lack scheduling sophistication. What might we call lazy scheduling, categorized by us as algorithm-level execution and stage-level execution, which we'll illustrate in detail later. Now let's walk through a typical hierarchical reduce algorithm. It has 4 stages. The stage 1, intranode reduce scatter within each node. GPUs reduce corresponding chunks so that each GPU holds a partially reduced piece within each group. And stage 2, internodes reduce scatter. We now reduce across nodes so that each node ends up with a globally reduced chunk. And stage 3, internode altogether. Nodes exchange these globally reduced chunks so that every node collectively holds all the fully reduced data. And stage 4, internode altogether. Finally, within each node, each GPU broadcasts the globally reduced chunk it holds. This hierarchical approach is common, but its efficiency depends heavily on how these operations are scheduled. To handle larger data volumes, communication algorithms process data in macro batches. Macro batches in here is only focused on the communication streams. This means breaking the workload into smaller chunks and processing them iteratively. Each macrobatch is allocated a data buffer consisting of multiple chunks, while the computation and the communication streams overlapped dependency between chunks ensure correctness and synchronization. Now, let's examine how existing solutions handle execution granularity in runtime. We present an abstract execution sequence of the runtime model for the previously described example. First, we define two types of dependencies, data dependencies and communication dependencies. The data dependency occurs when primitives processing the same chunk must execute in a specific order to avoid data consistency issues. For example, send operations S0 depends on the receive operation R0. And communication dependencies arise when too many thread blocks execute primitives on the same links, leading to bandwidth contention and performance degradation. We will illustrate it later. Now, we will look at the processing of the algorithm level execution. In it, one thread block is assigned to one GPU link. This approach is only repeated the execution logic offered by algorithm without any scheduling. Introduces significant bubbles idle time due to TB blocking and primitive dependencies. And the second tab, stage level execution, uses multiple thread blocks per link to avoid bubbles. Unfortunately, it leads to thread competing for bandwidth, resulting in poor resource utilizations. And let's look at that. Here, this is where ResCCL shines. Our approach introduces a new primitive level execution model by scheduling primitives at a finer granularity. ResCCL eliminates pipeline bubbles and maximizes bandwidth utilization through continuous dependency-free primitives called across macrobatches. Rather than binding thread blocks to links or stages, we schedule individual communication primitives across a fixed minimal set of thread blocks. This resource-efficient scheduling ensures both performance and GPU thread scalability. So how does ResCCL achieve this? The first step is to write the collective communication in our ResCCL language, a high-level domain-specific language. Each algorithm is represented as a dependency stack that captures inter-chunk dependencies sub-pipelines and then generate from these dependencies to maximize parallelism. Finally, this pipeline is scheduled efficiently to optimize the communication and the computation flow. ResCCL seamlessly integrates algorithm design with execution optimization. In essence, we break down the algorithm's original pipeline, reassign dependencies at a finer granularity, and scheduling dependency-free primitives across macrobatch earlier to fill ideal periods caused by blocking execution thread block. Let me walk you through a ResCCL language example. Here, we define a simple hierarchical algorithm. By iterating over nodes rank steps, we create transfer tasks between GPUs. Each task specifies which data chunk to send, where to send it, and whether to perform a reduction along the way. Next, we instantiate the primitive. The DSL generates an intermediate representation. The step value determines the execution order of primitives. Primitives processing the same chunk activate data dependencies. From the list of transfers in IR, we build a DAG. The edge represents data dependencies. A primitive can only execute after the primitives it depends on have finished. We then scheduled this DAG by splitting it into sub-pipelines, each handling a different macro-batch or chunk. Primitives operating on different links are color-coded for clarity. Those satisfying all dependencies are grouped into sub-pipelines for parallel execution. When assembling to the next stage, we eliminated all dependency-free edge and iteratively placed dependent primitives into pipeline. The maximum parallelism is degree is 8, so we allocate 8 TBs. The remaining primitives exhibit communication dependencies with those already in pipeline, which we would cause performance degradation. Therefore, they must be scheduled in subsequent pipelines. This demonstrates our primitive level execution model. The key to performance improvement lies in fine-grained dependency analysis, which enables the construction of sub-pipelines. This results in a well-defined overall dependency timeline, allowing back-to-back execution of the same primitives across different macro batches. Primitives are scheduled to stagger macro batches while satisfying dependency constraints with the pipeline execution. Now, on to our results. ResCCL delivers significant performance improvements. We achieve up to 2.5 times higher algorithm bandwidth compared to state-of-the-art libraries like Nico and Mexico. This translated to a 39% improvement in end-to-end training throughput for real workloads. Crucially, we also met our resource-efficient goals. Thread block consumption was reduced by up to 77.8%, and thread block utilization increased by 41.6%. This means less interference and more resources available for computation. In summary, we've shown that the key bottleneck in modern collective communication libraries isn't just the algorithm, it's the execution. ResCCL introduced a fine-grained primitive-level scheduling method that maximizes bandwidth efficiency while minimizing resource consumption. It's a practical and effective solution for accreting large-scale distributed training. Thank you for your time and attention.
Thanks. Again, interesting. Yeah, it was interesting seeing a sort of language-based approach and language compiler pipeline optimizing. So it's kind of cool. If one of the things I think is interesting in a lot of this work is it reminds me of when people started having deep pipelines on processors. They're just CPU design, and then you have to think about how you actually do instruction generation. So it's the same class of problem in computer science, except now it's very large scale instead of just on one chip. Any questions out there? Everyone's desperate for coffee, I see. Oh, there's a question here. Yeah, can somebody bring a mic down?
Hello?
Or is there one further back? Oh, there's one further back. Okay, sorry, yes.
Yeah, hi. This is Siva Kakala from Microsoft Research and an author of TECCL. From the example that you presented, I was wondering whether every node has to be identical and the topology is homogeneous and symmetrical. Does your framework handle the scenarios where it is not?
Sorry, please slow down. My listening is not very well.
From the example you presented, it felt like every node is identical and the topology is symmetric and homogeneous. Is it the case that your framework can handle only those, or can you handle topologies which are not replicas of, like, each node is not exactly the same?
Sorry, can we offline?
Yeah,
okay.
no worries.
Sorry.
There's one down here. Somewhere here, yes. Thanks. It's a race to get the microphone there. Thanks.
Hi, I'm Sai from Meta, and I have a question on the dependency graph. How do you pre-create dependency graph for bigger models?
Okay. Do you talk about the scheduling? The dependency graph. Sorry, I don't misunderstand all the sentences.
Yeah, it maybe we take the question in the coffee break.
Okay.
I think maybe easier one-to-one because the acoustics here are not great either, so we can go through multiple explanations and so on. Yeah.
Okay,
If that's
sure.
okay. I mean, I get the question, both the questions, but I think it'd be easier to do that one-to-one. Yeah, okay. Let's thank all the speakers for keeping to time as well. Really awesome. Good slides. All great.
Okay.
And thanks to everyone for staying here and asking questions. And see you out there with.